Hello everyone and welcome to Pepcoding. I hope you all are extremely good. So today in this video we are going to discuss another question on graph, that is to remove maximum number of edges to keep graph fully traversable, right? So in this question we are given an undirected graph of n nodes and we are given three types of edges, right? So type 1 edge can be traversed by Alice only, type 2 edge can be traversed by Bob only, and type 3 edge can be traversed by both Alice and Bob, right? So we have to do what, that we are given an array of edges, right? So the first column like this. So the first column is representing the type of edge, right? For example, this column is representing that this edge is of type 3, that is this edge can be traversed by both Alice as well as Bob, right? The next two are the source and the destination, right? So an edge from 2 to 3 is of type 3, that is there is an edge present from 2 to 3 that can be used by both Alice and Bob, right? So what we have to do, find the maximum number of edges you can remove so that after removing the edges the graph can still be fully traversed by both Alice and Bob. The graph is fully traversed by Alice and Bob if starting from any node they can reach all other nodes, right? Return the maximum number of edges you can remove, or return -1 if it's not possible for the graph to be fully traversed by Alice and Bob, right? So for example, we are given this array, that is 3 1 2 3 2 3. Next is 1 1 3 1 2 4. Next is 1 1 2 2 3 4. Now this column is representing the type of edges and this is representing the source and this is representing the destination of the edge, right? So let's draw a graph on the basis of given edges. So there are 4 vertices present here, right? So let's color the type 3 vertex with blue, that is they can be visited by both Alice and Bob, right? Let's color type 1 edge with red, that is they can be visited by Alice only. And let's use green color for type 2 edge, that is it can be used by Bob only, right? So the first edge is from 1 to 2, that is of type 3. The second edge is from 2 to 3, that is of type 3. The third edge is from 1 to 3, that is of type 1. The fourth edge is from 2 to 4. Fifth is from 1 to 2. Next is from 3 to 4, that is of type green, right? So now this edge is representing that both Alice and Bob can go from 1 to 3. This is representing that by using this edge only Bob can go from 3 to 4. Why? Because this is of type 2, right? So what we have to do, we have to find the maximum number of edges that can be removed from this graph, so such that after the removal of that edges this graph is still fully traversable for Alice as well as Bob. Now fully traversable is that if Alice is starting from this vertex, she can go from all the vertices of this graph. For example, now Alice can go from 1 to 2 by using this or this vertex, right? Now Alice can also go from 2 to 3 by using this edge. Why? Because Alice can use this edge. This is of type 1, right? Now Alice can go from 3 to 4. How? By using these edges. That is by using this path, right? So this is fully traversable for Alice because Alice can go from any of the vertex to all the vertices of this graph, right? Similarly, Bob can also go from one vertex to all the vertices of the graph. Now we have to find the maximum number of edges that can be removed from this, such that after the removal of that edges the graph is still fully traversable for both Alice as well as Bob, that is the graph is connected for both of them, right? So how can we do this? we have to draw a DSU for both Alice, DSU for Alice and for Bob, right? So we have to draw the DSU for both Alice and Bob, right? So let's the DSU for Alice is initially all the vertices are unvisited, right? Also we have to take a count variable. Why? Because we want to count that if all the vertices are visited by them or not, right? Also we are using another variable, that is remove as. Now we will store in this, initialize these two also 0. Now we will store in this the edges that can be removed from this, such that after the removal the graph is still be traversable, fully traversable for both Alice and Bob, right? So also one thing to note here is that the preference for type 3 edge is always more than 1 and 2. Why? Because type 3 edge can be used by both Alice as well as Bob to go from one vertex to another, right? So if I can use this edge, this is of type 3 edge, if I can use this edge to go from 1 to 2, then clearly this is an extra edge. I can remove this. Why? Because Alice can go from 1 to 2 by using this edge only, right? So the preference of type 3 edge is always greater than 1 and 2. So before doing this, we have to sort this array on the basis of the 0th column, such that we get 3 before 1 and 2, right? So sort this array before finding the DSU for Alice and Bob, right? So we will find the disjoint set union for Alice and Bob, right? So first of all, let this is already sorted. We only want 3 before 1 and 2. Now after that 1 and 2 can be in any order because the preference for both of them is same, right? So we'll start from this edge. So this edge is connecting 1 and 2. So in the DSU, add this edge and also add the vertices to this variable, right? So by using this edge we are able to visit 2 vertices. So add 2 vertices to this. Now this edge can be used by both Alice and Bob. So add this edge to the DSU for both Alice as well as Bob, right? So we are using this edge, so we can't remove this edge. So we are not incrementing, we are not changing the remove edge variable, right? And next edge is 3 type 3, and this is joining 2 and 3. Now this edge is not already present in the DSU, so add this edge. So this is joining 2 and 3 for both Alice and Bob. Now it is adding one more vertex to our count variables, that is one vertex now can now be visited by using the edges, right? So add this to the DSU. Now since we are not removing these edges because this edge is useful for us, so we are not changing the remove edge variable, right? So next move to this edge. Now this edge can be used by Alice only, and this is for going from 1 to 3. Now we have to add this edge to the DSU for Alice, but we are seeing that this edge is already present, that is a path from to go from 1 to 3 is already present in the DSU for Alice. So this edge is not useful for, so we can remove this edge. So we have to increment the remove variable, that is we have found an edge that can be removed from this. Why? Because Alice can visit Alice can go from 1 to 3 by using the edge that is already present, right? So next is this edge 2 to 4. Now this edge can be used by Alice only. Here there is no path present to go from 2 to 4. So add this edge to the DSU for Alice and add a vertex, since because now one more vertex is visited by Alice, right? So add this vertex. So we are not removing this edge. So the remove edge variable remain unchanged, right? The next edge is to go from 1 to 2. So by using this edge, Alice can go from 1 to 2, but So we have to add this edge to the DSU for Alice, but in the DSU there is already a path present to go from 1 to 2, right? So this edge is not useful, so we can remove this edge to increment the remove edge variable by 1, right? So next edge is to go from 3 to 4. Now this edge can be used by Bob to go from 3 to 4. Now there is no edge present in the DSU of Bob to go to vertex 4, right? So add this edge to the DSU to go from 3 to 4, right? Now since you are adding this edge, so increase the vertex count by 1. Now we have traversed all the edges. Now you can see in the DSU for Alice and Bob that Alice can traverse all the vertices of the graph. Bob can also traverse all the vertices of the graph even after the removal of two vertices, two edges, right? So you can also confirm it from here that since this is 4, this is also 4. The total number of vertices present in the graph is also 4. So all the 4 vertices can be visited by Alice as well as Bob by using these much number of edges and by after removing these two edges. So we have to return this answer, that is maximum of 2 edges can be removed from this graph such that after the removal of these 2 edges the graph is still fully traversable for Alice as well as Bob. So we can remove this 1 to 3 edge and 1 to this edge, right? So the graph is still fully traversable for Alice as well as Bob, right? Now there is no method by using which you can increase this number, because the maximum number of edges that can be removed from this graph is 2 only, right? So what we were doing, we are creating the DSU for Alice as well as Bob, and we are taking a control over the two variables, that is count A and count B, right? If after traversing all the edges, if we are able to visit all the if Alice and Bob both are able to visit all the vertex of the graph, then this means that we can remove this much number of edges, right? So let's now move to the code part. So we are going to create the DSU for Alice and Bob, right? So we are using the find and the union function of the DSU. So let's first create the find function. So we have to create it before this, right? So find, we are passing the vertex and the parent, right? The ancestor. The name of this is parent. Right? Next, else. If the parent is the vertex itself, then return that, else find the parent. And add that to the parent array. And return the ancestor, right? So this function is going to return the ancestor of a particular vertex of the graph, right? So next we are going to use the union function of DSU, right? So union, let's use boolean here such that this function will tell if we are able to merge the two edges or not, right? So the source and the destination, the two arrays, right? The parent array and the rank array. Rank, right? So now let's write this function. So first find the ancestor of x, that is the leader of x, that is x, and pass the parent. Find the leader of y, pass y and the parent. Next, check if leader of X is not equal to leader of Y, that is the ancestor of both are not same, then return true. That is we can merge these two edges, right? So this means that now true is showing that the edges are not already present, the vertex are not already present in the DSU, so add that to the DSU. And false is showing that the vertex are already, there is already a path to go from that two vertices in the DSU, right? So there is no need to add that, right? So here we have to check that if leader of X is less than leader of Y, then parent of leader of X is what? Leader of Y. Else if leader of Y is less than leader of X, and parent of leader of Y is leader of X, right? So here we are what? We are drawing the DSU, right? Else parent of leader of X is leader of Y. The rank of leader of Y is, increment the rank of leader of Y by 1, right? So this is the union function in order to draw the DSU. Find the DSU of for Alice as well as Bob, right? So this is our main function. Here we have to use 4 different vectors, right? So let's define the 4 vectors. Each of them are of size n plus 1 by, because the number of vertices given in the graph are starting from 1, right? So this is of 1 n plus 1. This one is for Alice. Create one for Bob, right? This is also of size n plus 1. Next we need the rank array. So let's create the rank vector for A. Let's firstly initialize them to 0. Now rank of all the vertices is 1 for initially, right? So next fill this parent array, right? Parent P of Y is I, right? So we have filled the parent array for both Alice and Bob, right? Our next step is what? Our next step is to traverse in the H vector, right? So we have to traverse in the H vector, right? Here edges, right? So next is we have to check the type of the edge first, right? If the type of the edge is 3, this means that we have to check in the DSU of for both Alice and Bob, right? So if firstly we will check the type of edge. If the type of edge is 3, then we have to do something else. Else if the type of edge is 1, type of edge is 1, else it is obvious that the type of edge is 2, right? So if the type of edge is 3, this means that this edge can be used by both Alice and Bob. So we have to find it in both in the DSU for both Alice and Bob, right? So we will check that if we can merge these two or not, right? So we will check this, pass the source which is present in the first column, pass the destination which is present in the second column, and pass the two parent and the rank array for Alice. The same thing for Bo. The DSU for Bo. The destination, the parent of Bo, the rank of Bo, right? So next, if the temp A, that is for this check, for this edge, if we are it is returning true, that is we have to add this edge to our DSU, that is this edge is useful, we can't remove this edge. So we are doing what, that if this edge is useful, then increase the count of A by 1. If this edge is useful for B, then increment the count of B by 1. So we have to take these two variables also. So let's take these two. Let's name this as merged A and merged B. Also we need one more variable, that is remove edge, that will contain the number of edges that can be removed, right? So I have initialized them with -1, because when we are merging two edges, then one of the vertex is already present, right? So when I am merging the one edge, then two of the vertices are covered in this, right? So I have initialized it with 1, right? So if it can be merged, that is if temp of A is true, it is returning true. This means that merged of A increment the count of A by 1. If temp B is also returning us true, that is if this edge is useful for Bob also, then increment the count of B, count for B by 1. Merged, oh, spelling of merged is wrong here, merged, right? Merged of B. Else if both the values are false, that is both are already present in the DSU, then we can remove that edge. So increment the count of remove edge by 1, right? So this is for the type 3 edge, that is for both Alice and Bob. If the edge of type is 1, that is it can be used by Alice only, so we have to check in the DSU of Alice only, right? So we will implement this for Alice. If it can be added, then add it, else increment the number of remove edge by 1, right? The same work is to be done for Bob also, right? Now this is for Bob, so pass the parameters for Bob. Right? Now when this for loop is terminated, that is we have traversed all the edges, that is the entire array. Now we will check the count of A and count of B. If both of them are equal to the number of vertex in the graph, then this means that we are able to find the number of remove edges, that is they can be removed. Even after removal of them, the graph is fully traversable for both Alice and Bo. But if any of them is not equal to the total number of edges, this means that the graph is not fully traversable for Alice and Bo. So this means that we have to return -1 in that case, that is graph is not traversable by Alice and Bob, right? So after this for loop, we will check the count of A and B. So we will check if merged A is not equal to n or merged B is not equal to n. That is either of them is not equal to n, then return -1. Else we have to return what, the number of remove edges, right? So this is the code, but firstly we have to do what, that we have to sort this 2D array on the basis of first index, right? So you can use this function, right? You can see that how to sort the 2D array on the basis of the first column, right? So sort edges dot begin, edges dot end, sort, right? Since here index 0 is passed, so it will sort the given array on the basis of the 0th column, right? right? So I think the code is correct. I have to use the syntax of C++ here. Oh, right. So let's try to run it. Some compilation error is there. The union function inbuilt is also present in C++. So let's change the name of this union function to something else. So let's change this to union 1, right? So we have to change it here also. Here and here, right? So let's again try to submit it in line number 58. Here the name of the variables are temp A and temp B, right? So now we are getting the correct answer, right? So let's try to submit it. So our code is passing all the test cases, right? So this is how we can find the maximum number of edges that can be removed from the graph such that the graph will remain fully traversable for both Alice and Bob, right? So what we are doing, we are finding the DSU, that is disjoint set union for both Alice and Bob by using the find and the union function, right? By using this find and the union function. Next, we are checking if we can remove the edge or nodes, right? So if we can't, then we are adding that to the DSU and incrementing the number of vertices, right? If we can remove the edges, then we are incrementing the remove edge variable, and in the end we are checking that if the graph is fully traversable by both Alice and Bob. If it is, then remove the number of edges, else return -1, that is the graph was not fully traversable for both of them, right? So this is the problem. I hope the problem is clear to you. So don't forget to like this video. Thank you for watching.